Hey students, welcome to lecture number 5 of Linear Algebra 1. So last time we introduced the notion of a linear map, and today we want to talk about special linear maps which have some kind of a geometric interpretation. So let's first recall what was a linear map. So a linear map was a function or a map from Rn to Rm, and for f to be linear it needs to satisfy two conditions. So the first condition was that whenever I have two vectors, so let's u and v be vectors in Rn, then if I consider the f of the sum of u and v, this is the same as first applying f to u, so this is a vector in Rm, plus f of v. And the second condition was that if I have a scalar, some real number lambda, then I can multiply this scalar with u, which also gives a vector in Rn, and then applying f is the same as first applying f to u, which is a vector in Rm, and then I can multiply with lambda. And we saw a few examples of linear maps last time, and we also saw that any linear map can be described by multiplying with a matrix. So in other words, if I have a linear map f, then I can always find a matrix which we denoted by these square brackets of f. So this is a matrix, so this is the matrix of f. And this was an m by n matrix with the property that the value of f of x is exactly given by multiplying with this matrix. And today we will do some examples of linear maps, and usually it's not clear how to find these matrices. So maybe in these examples it was quite easy, but today we will see that, for example, in the definition of a projection, it's not so obvious at all at the beginning how this matrix looks like, and this will also be part of your homework. Okay, so let's start. We consider first this linear map. So we have a function from R2 to R2, and it sends this vector x1, x2 to this vector here, minus x2, x1. And the first statement is that this is a linear map. And how do we check this? Well, we could check these two conditions here. Or what we also learned last time is we could also show that there exists a matrix such that the value of f of x is given by multiplying with this matrix. And then you showed that multiplying with the matrix satisfies these two conditions here. So in this case here we can say this is a linear map because the value, so this here is f of x, but this can also be written by multiplying with this matrix here. And then this here is the matrix of f. And because we can write f of x as multiplying with some matrix times x, then we already know this is a linear map. So now let's see what this linear map does. So if we start with some vector here, x1, x2, so let's say this here is, I draw this vector here in R2, so here I have x1 and x2. Then if I apply this linear map to this vector x, then I get this vector here, where now I have the first coordinate is minus x2 and the second coordinate is x1. And here in this picture you can already see what happens. So here we get a rotation by 90 degrees, but let's actually check that this is the case. So here I draw two triangles, this triangle and this triangle. And first you notice that this angle here is exactly the same as here, because this length of this triangle is exactly the length of this triangle, and this length here is exactly the length of this triangle. And also this angle here, which I denote by beta, is given by this angle here. And the remaining twos are just 90 degrees. So what we want to show is that this is actually a rotation by 90 degrees. So what we want to show is that this angle here is actually 90 degrees. And for this, what do we do? So we see here that this beta plus this gamma plus this alpha is exactly 180 degrees. So we have the equation that beta plus gamma plus alpha is 180. Or we can also write, if we use radians, this is pi. And but we also have that alpha and beta are here in the same triangle, and here we have 90 degrees. And we know the sum in a triangle is always also 180. And therefore alpha plus beta is also 90 degrees, which is pi half. And combining these, we see alpha plus beta is 90 degrees, and alpha plus beta plus gamma is 180, and therefore we see that this gamma is indeed 90 degrees. And therefore we see that this map actually really rotates counterclockwise by 90 degrees. And we see that this vector here and this vector, so here we have 90 degrees, and we say that these two vectors are orthogonal to each other. And now we might ask, how can I check in general if two vectors are orthogonal to each other? So maybe in R2, this is quite easy. So you see that here maybe they are always orthogonal. If I have a vector, then this vector is orthogonal. If I take the second entry with a minus sign and the first entry here with a plus sign, or I could take the negative of this, so it could also show in this direction, then I also have 90 degrees. But in R3, maybe this is difficult to describe, but there's a really easy way of telling if two vectors are orthogonal to each other or not. So, but first we write down that this f is a rotation by 90 degrees counterclockwise. And we also notice that f of x and x are orthogonal, meaning the angle between these two vectors is 90 degrees to each other. And what we want to introduce now is this notion of orthogonal in general in Rn. So maybe in R2 and in R3 we have some geometric understanding what we mean by 90 degrees. But actually there's a notion for any Rn, even though we cannot imagine what vectors in Rn look like. But we will define this by using the so-called dot product. So this is the first thing we want to introduce today. So if I have two vectors, u and v, with entries u1 up to un and v1 up to vn, so these are both vectors in Rn, then what we define is the dot product of u and v. So we define a product of two vectors, and the notation is that we use this thick point here. So don't get confused with the usual multiplication point. So this is really a thick black circle. And the definition is that the dot product of these two vectors is this number where we take a u1 times v1 plus u2 times v2 up to un times vn. So this here is really a real number. So if I take two vectors, vector with a dot product of another vector, which needs to be the same size, then this gives a number. And with this, we can now define the following. Now we say that two vectors u and v are called orthogonal if the dot product of these two vectors is 0. And why does this have to do with what we saw before? I mean, here we call this orthogonal because the angle between them is 90 degrees. But actually one can show that this is exactly the case when the dot product is 0. Because here, what is the dot product of x1, x2 with this minus x2, x1, well, by definition the dot product is this entry times this entry plus this entry times this entry. So here it's x1 times minus x2 plus x2 times x1. Well, in this we see here is 0. So in this case actually the dot product is 0 and therefore they are orthogonal. But also, well, this we will not show, but in R3, so if I have two vectors in R3, then this dot product is also defined. Then I have a sum of 3 terms here, and it is the case that if the dot product of these two vectors are orthogonal, is 0, sorry, then these two vectors are orthogonal, meaning if I draw them in R3, then the angle between these two vectors is 90 degrees. But here we define it for any vectors in Rn, so we also can talk about vectors in R10, which are orthogonal to each other, even though we cannot imagine what it means for vectors in R10 to be orthogonal to each other. And using this dot product, we also define the so-called norm of a vector u. So the norm of u, where we use this notation here with these two lines of u, is given by the square root of the dot product of u with itself. And this, the dot product of u with u, is just given, I just multiply u1 with u1 plus u2 with times u2 and so on. So this is just the square root of the sum of the squares of the entries of this vector. So if I have a vector, for example, let's say I have u1, u2, then here I have this length is u1, this length is u2, and in this case, what is the norm of u? The norm of u is exactly given by the length here, because using Pythagoras, we see that this here, the square of this equals this square plus this square, so therefore if I take the square root, it's exactly this length here. And also in R3 you can check that the norm of a vector in R3 is exactly the length of this vector. So sometimes we can also just say this is a length. But again, in R4 and so on, maybe it's hard to imagine what we mean by length. Okay, so maybe some remarks here. So the dot product allows us to talk about angles, well, in general we can talk about the length of a vector and angles in Rn, even though we cannot imagine this. So for example, if n is 2 or 3, then if I draw these vectors u and v, then I can make sense of this angle here, let's call it alpha, and then one can show that the cosine of this angle, if I multiply it with the norm of u and the norm of v, then this is exactly given by the dot product of u and v. So maybe if you are bored and you have time, you can maybe check that in R2, if you start with some vectors v and u, and you calculate this angle here, then the cosine of this angle is given exactly by taking the dot product of these two vectors and divided by the length, by the product of the norms of these two vectors. But so this interpretation as an angle just makes sense for us for the case 2 and 3. But for higher n, this is actually that this can be used to define what we mean by an angle, we then define the cosine of an angle between two vectors by taking the dot product divided by the product of the norms, because these two notions make sense for arbitrary n. Okay, but this is just a remark, and also another remark is that in this dot product is also sometimes called scalar product, or inner product. And also in linear algebra 2, we will talk about vector spaces, and these Rn's are just special cases of vector spaces, and other examples of vector spaces are, for example, the space of continuous functions or the space of polynomials. And for these vector spaces, there's a general notion of what we mean by a scalar product. And then we can also say that two elements in the vector space, for example, two polynomials, are called orthogonal to each other, even though this doesn't make sense from a geometric point of view. They are called orthogonal if their scalar product of these two vectors is 0. And then we can also talk about the norm of a polynomial. And this has a lot of applications. But in linear algebra 1, we stick to this Rn, because already in Rn we can do a lot of fun things. Okay, and also another comment, another way of writing, oh sorry, this is not the dot product, this is just the points of the remark. So we can write the dot product in another way. So for this we use this notation here. So U is a vector in Rn, and UT, T stands for transpose, just means that this U, which is a vector of size n, so it's a n times 1 matrix, we just flip around to make it a 1 times n matrix. So in other words, we get a row vector with entries u1, u2 up to un. So this is a 1 times n matrix. And with this, we can write the dot product of u with some vector v. So this is the dot product in a different way, because ut, which is a 1 times n matrix, this matrix I can multiply with a vector of size n, and the result will be a matrix of a 1 by 1 matrix. So in other words, this is just a number. But let's write this down. So this is this matrix times this vector. And you see that this is exactly here the same, because if I multiply this out, I get u1 v1 plus un vn. So this is, more precisely, it's a matrix of size 1 times 1. But this is just another way of writing the dot product. So the dot product can actually be written as a matrix times a vector multiplication. Okay, and now the dot product satisfies a lot of properties, which we will need later. So this is this proposition here, that, so we have these three statements. So let's take vectors u, v, and w in Rn and some scalar lambda. Then the first statement is that the dot product is commutative, which means that the dot product of u with v is the same as the dot product of v with u. But this is clear by definition, because here we see that it doesn't matter. The order here doesn't matter, because the product here is commutative. And then the second statement is that if I add two vectors, v plus w, and then, so this gives a vector, and then take a dot product with another vector u, then this is the same as first taking the dot product of u and v plus the dot product of u with w. And this you can also check by definition, that because the entries here are just given by the sums of the entries of v and w. And if you write this out, you get this expression here. And the third statement is that if I have some scalar here, so I take the dot product u with lambda times v, then I can also just first take the dot product of u with v and then multiply with lambda. So the proof is check by yourself, maybe just with a few examples, but it follows directly by the definition. So basically this means that the dot product somehow behaves like the usual multiplication of numbers, even though this is not the multiplication of numbers, it's a multiplication of two vectors and the output is a number. Okay, so and this notation of the dot product we will use later to define projection and reflection. And now, so we want to give a list today of several geometric linear maps. And the first one is quite simple. It's scaling. So what I mean by this is that if I have some factor lambda, let's say it's a positive number, then we can define the following map, which I denote by h lambda, and it sends a vector of Rn to a vector of Rn by just multiplying with this number. And why is this a linear map? Well, we could check these two conditions, but we can also try to find a matrix such that this map, this function here is given by multiplication with the matrix. And in this case, so what is the matrix of this? Well, multiplying a vector with lambda just means that each entry gets multiplied with lambda. So this here is just lambda x1 up to lambda xn. And how do I go from x to this vector here by which matrix? Well, the matrix I take is just the matrix which has lambdas on the diagonal and the rest is 0. Right? Because if I multiply a vector with this matrix here, then I just multiply each entry by this factor lambda. And this we can also write, this is lambda times this matrix, 1, 1. So we have everywhere 0 except on the diagonal. And this matrix we also give a name, and it also appeared before. So this is the identity matrix, which we denote by IN. So this is called the identity matrix. Okay, so this is a matrix of this linear map H lambda. Okay, so this is maybe not, well, it's some geometric linear map, because if I start with some vector and I multiply with, if I apply this linear map, then this just scales this vector, so it just increases the length of this vector, the norm of this vector. But a more interesting example is now the following. So what we want to do is we want to define the orthogonal projection to a line. And what I mean by this is that if I have a vector u, so we fix some u in Rn, and we want that this vector is not the 0 vector. And in the following, and also maybe in the homework, we will use this notation here. So if we know that a vector is if some element here is a vector in Rn, and we say u is not 0, then by this 0 we mean the 0 vector. So sometimes this is a common notation, because often you don't want to write this vector with just zeros, then we just say u is not 0. And this 0 is then the 0 vector. Anyway, so what we want to define is, if I start with some vector x, then I want to project this vector x to the line spanned by this vector u. So this red line here are all points which are on the direction of u, so these are all multiples of u. And we want to project a vector x onto this line. So even though this picture here is in R2, as this also makes sense in Rn. So if I have a vector u and I have another vector x, then I want to project this vector x onto this point here on the line of u. And how do we do this? So first, what we want. So we want to call this map pu, projection to the line spanned by u. And this will be a map from Rn to Rn. And we want to send x to, well, now we want to give this point here a name. So this blue part, this point here, we want to call x parallel. So this is here on the red line. And the difference here, so this green part here, we want to call x orthogonal. So this here is a symbol for orthogonal, and this is a symbol for parallel, because here this x is now parallel to u, this x parallel. So what we want to define is, starting with an x, we want to send x to this thing here. So we want to send it to x parallel. And so what is the condition on this thing here? So first of all, notice that the sum of this x parallel and this x orthogonal here, so here's, if I would add this x orthogonal, we get x. So so the condition is that this x is given by x parallel plus x orthogonal. And what do we mean by x orthogonal? Well, this vector here is orthogonal to u. And what does orthogonal mean? Well, we defined this to be, x, this vector is orthogonal to u if the dot product is 0. So the first condition is that the dot product of this x orthogonal should be 0. And what does this x parallel here means? This is that it shows in the same direction as u. So this means that this x parallel is given by some lambda times u. Right? Because all these points on this red line are given by multiplying u with some scalar. For example, here would be 2u, here would be minus u, maybe here would be 1/2 u, and so on. And for example, in this picture here, maybe this is 1.2 times u. Okay, so we want to find now a map pu, which sends x to this x parallel, where by x parallel we mean that this is some multiple of u, and the difference between x parallel and our x is orthogonal to u. And so we want to find, in other words, we want to find this lambda here, right? Because we want to send this x to lambda times u, and this lambda we now want to find, if it exists. So, so now consider u, the scalar product of u with x. I mean, this is the input we have here for our function, the u and the x. And now let's see what the scalar product of these two vectors is, assuming these conditions here. So x should be written as a sum of these two vectors here, x parallel and x orthogonal. X parallel plus x orthogonal. And now we use one of these properties in the proposition that if I take the scalar product of a vector with the sum of two vectors, then I can just use that I can take the scalar product of the first one plus the scalar product with the second one. So we have this. And now this x orthogonal should be orthogonal to u. That's why we call it x orthogonal. And therefore this here should be 0. And here, this x parallel should be given by some lambda times u. So what we get here is u scalar product with the unknown lambda times u. But now we can use the other property that if I take the scalar product of a vector u with scalar times a vector, then the scalar can go in front, and therefore this is lambda times u scalar product with u. And here, so this is the scalar product of these two vectors, u with itself, and so this gives a number, and this is a number, so this little dot here, this is just the multiplication of two numbers. And now, I mean, what did we want to do is, we wanted to find this lambda here, but now we see that if this exists with these properties here, then this lambda should satisfy this property that if I take the scalar product of u with x, then this should equal lambda times the scalar product of u with u. So in other words, let's define the lambda to be u scalar product with x divided by u scalar product with u. But of course here we need to be careful. We divide by number, so we should check if this lambda, if this number is not 0. But this is the case because here we assume that this vector u is not 0, and recall the scalar product of u with itself is given by this sum here. So if u is not the 0 vector, then there are some entries. They can be positive or negative. But if I take the square, then everything here becomes positive. And therefore, if u is not the 0 vector, then this here is a positive number. So it's, in particular, it's not 0. And therefore, oops, I'm too fast here. And therefore, if this vector is not the 0 vector, this number here is also not 0. So this here is not 0. Because u is not 0, where this 0 is the 0 vector, and this 0 is the real number 0. So, and this is now our definition of this map here. So we want this to be lambda times x. So we will take this lambda here to define this linear map here, even though we don't know yet if this is a linear map or not. But so this is our definition. So we define, so if we have a vector u which is not 0, again this 0 here is the 0 vector, then we define the orthogonal projection pu onto this line spanned by u by sending x to this vector here. So this is a number, because this is a number, this is a number, times the vector u. And therefore this here is a vector in Rn, and it's given by some multiple of this vector u. And why does this satisfy the condition we wanted to have? So first, so if I have, let's say here I have u, oh, that's not beautiful. Let's say I have u here. So this is a line spanned by u, and here I have x. Then we want that this here is actually our pu of x. So in other words, what we should have is that the difference here, pu minus x, which gives this vector here, or x minus pu, is orthogonal to u. And so we can, so what we get here, that this vector here, so this is what we called before x orthogonal. So we can check now by this definition that if we take the dot product with u, then by this definition here, so we can plug in, this is well, first of all, we can again use this property that we can first take the dot product x with u minus, and now we can use the definition of this, u times x divided by u times u. Okay, get rid of the thing here. So we take the dot product of this. So here on the left we still have x times u. And here, so this is just a scalar, which we can put in front. So here it's really just u x, u times u. And here we now take the scalar product of u with u. And we see this number we can divide out here, and we have x times u minus u times x, which is 0. So we really have that after this map here, this image, well, this value here, the difference between x and this is orthogonal to u. So this is really the orthogonal projection of x onto this line of u. And you can also check that if something is on the line of u, so if I have that some vector is a multiple of u, then this pu of x will be just the same. Because if you plug this into this formula, you will see that you get exactly x in the end. And also the image of this map here, well, what is the image? Well, clearly the image is the line of u, because here we see that everything we get out of here, out of this function, is always a multiple of u, and therefore the image of this pu is given by all x in Rn, which are given by some multiple of u. Or maybe one should say there exists a lambda in R such that this x is just given by lambda times u. Another way of writing this, we could also say these are all multiples, oops, like this. Okay. But now, is this a linear map? Well, we can again check either that these two conditions are satisfied, but so from the geometric interpretation, this we can check. For example, if I take a vector x and project, if I take, let's say, two vectors, let's say u and v, and I take the orthogonal projection of v and the orthogonal projection of u, then the statement is that if I first add these two vectors, here I get the orthogonal projection of u plus v. This is the same as taking first the orthogonal projection and then add these 2 points to get this one. And the other statement is that if I multiply with a factor, let's say here I have 1.5 times x, and if I take then the orthogonal projection, then this orthogonal projection is also 1.5 times this orthogonal projection here. But this we want to check now explicitly. So the statement is that for any u which is not 0, this orthogonal projection pu is actually a linear map. So let's prove this. So let's take two vectors, x and y. And I'm sorry, I call them x and y now and not u and v. So what is pu x plus y? Well, by definition of this map pu, this is the scalar product u with x plus y divided by scalar product u and u, and this multiplied with u. And now we can use the property of the scalar product here. We can first take the scalar product with x and then the scalar product with y times u. But this we can just split up into ux uu plus uy uu times u. But this is the same as u times x, u times u, u, y. And this is the definition of pu of x plus, and here we have pu of y. So therefore we have this property, the first property of being a linear map, and the second property is similar. So if I have some lambda, then what is pu of lambda x? Well, by definition it's u times lambda x divided by u times u. And here again we can use a property that this lambda can go in front. So it's lambda times u x u. But here this lambda we can also put completely in front. So this is then just lambda times pu of x. And this proves the second property for being a linear map. Okay, and in the homework you will write down the matrix of this linear map, because now you see here in the definition it's not clear why is this some matrix times x. Here in this matrix of this linear map pu you will calculate in your homework. Because here it's some number times the vector u, and this number contains this x. But this is, a priori it's not clear how to write this as a matrix times a vector. But in the homework you will see that there's an explicit matrix which just depends on this u, which you can write down, and then this expression here can be written as this matrix times x. And this would then give another proof of this proposition here, that this is a linear map. Anyway, let's do an example. So let's take the case n equals 2, so we can draw things. And let's take as a vector u the vector 1, 1. And then the line spanned by u is just given by this diagonal here. And what we want to do is we want to calculate now the orthogonal projection of some x. Let's say here's x, and here's pu of x. And this we want to do explicitly. So what is pu of x? Well, again, the definition is ux divided by uu times u. And now let's first calculate these things here. So if I have an arbitrary x like this with entries x1 and x2, and I take the dot product with u, so what is this? Well, the dot product is just this entry times this entry plus this entry times this entry, and therefore this is just x1 plus x2. And so this would give this entry here. And what is this entry here? Well, this is just the dot product u with u. So it's just 1 times 1 plus 1 times 1. So it's 1 squared plus 1 squared. So this equals 2. So therefore we can plug it in here. So the numerator is x1 plus x2. This is a number. And the denominator is 2. So it's x1 plus x2 half times a vector. And the vector is u, which is 1, 1. And therefore this gives the vector x1 plus x2 half, and here x1 plus x2 half. And this we can now write as a matrix times the vector x, because if I take this matrix here, 1 half, 1 half, 1 half, 1 half, then this vector here is exactly multiplying this matrix with the vector x1, x2. And therefore this here is the matrix of Pu in this explicit example of U. So now let's take a really explicit value for x. So for example, this point here, so this is the point 1, 1, 3. Also vector 1, 3 is this one here. So what is Pu of 1, 3? So let's calculate this. Pu 1, 3. Well, we multiply with this matrix. 1, 3. And what do we get? Well, it's 1/2 plus 3/2 is 4/2. So this is 2. And, well, here it's the same, so it's 2, 2. And where is 2, 2 here in the picture? Let's take purple. 2, 2 is here. Well, and we see, so this is Pu of 1, 3. And we see here that this is exactly, if you would draw this line here, then we see that the angle here is exactly 90 degrees. So here the orthogonal projection of this vector 1, 3 onto this line spanned by the vector 1, 1 is given by 2, 2. Okay. And now we had this notion of injective, surjective, and bijective and image. So the image of these orthogonal projections are always given by this line spanned by U. And is this map injective? Well, of course not, because for example this point here would also get mapped to this point here. So in this case here we see that this map is not injective, and clearly it's also not surjective, because for example this point is not in the image because it's not on the line spanned by U. But there's one exception, namely the case n equals 1. In this case, everything is a little bit boring, because in the case n equals 1, everything is just a number. So in the case n equals 1, so we finish the example here, this is just a map from R to R, sending the number x to U dot product x. But if U and x are elements in R1, then the dot product is just the usual multiplication of numbers. So in this case, it's just the usual multiplication of U and x. And in this case, U is a non-zero number. And here we have U times U. And this we multiply by U. And you see, and because now this is just multiplication of numbers, we can cancel out these U's. So this is just x. So in this case, this Pu is just the identity map. In the special case, n equals 1. In the case n greater equal to 2, so in particular, in this case, Pu is bijective. But in the case n greater equal to 2, Pu is not injective and not surjective. Yeah, and this you can see because anything which is not on the line spanned by U is not in the image, therefore it's not in surjective. And you can always, if you start with something which is not in the image, for example this point, you can take, for example, this point which is here in between these two, and therefore these 2 points here gets mapped to the same. So it's also not injective. Okay, and now the next example. Now, so we did a projection, and now what we want to do is reflection. And what we mean by this is now, instead of projecting x onto the line spanned by U, we want to reflect this by the line of u, meaning we want to send it on the other side of this line. And this is what we call reflection here. So we want to define rho. So this is a rho, Greek, rho. Rho u is now a map from Rn to Rn. And how is rho u of x given? So with the same notations as before, we have the line spanned by u here, we have x, and then we have this x transpose, the x parallel, sorry, which is orthogonal to u, and here we have the projection of x onto the u, or this we also called before this x parallel. And what we want now is from x we want to go here, so what we want to subtract from x is 2 times this x orthogonal, right? Because subtracting 1 times will go here to the projection, and subtracting it another times will go on the other side of the line spanned by u. So this p of x we want to define as follows. It's x minus 2 times this x orthogonal. And recall, this x orthogonal was given by x minus pu of x. So this green line here is this minus this, right? Because here we can go from x to this x orthogonal by subtracting pu of x. And pu of x we described before explicitly. So let's remember this. So we can write this as x minus 2 times x minus pu of x. And in other words, we have 2 times pu of x. And here I have x minus 2 times x. So here it's minus x. And this expression you can also see in the picture, because to go here we can either start an x and subtract twice this x orthogonal, or we could take 2 times pu, so here is 2 times pu, and then we can subtract this x here, so here is minus x. You see that this here is parallel to this line here. So this formula you can also see here in the picture. This reflection of x along the line spanned by u is given by taking twice the projection of x onto u and then subtracting x here. And now we can use the explicit formula we had before. So this is 2 times u x u minus x. And this will be the definition of this reflection. So this is given here. So this here now explains this maybe first complicated looking formula. So again, this u shouldn't be the zero vector, and then we define the reflection along the line spanned by u as this linear map here. And you will show in the homework that this is indeed also a linear map. And this again you can do in 2 ways. You can check these 2 conditions, or you can write down an explicit matrix, which you will also do in the homework, such that this expression is given by some matrix which will just depend on u times the vector x. Okay, so let's do an example. So let's take again the diagonal. So here we have again u on the diagonal, 1, 1. And here we have the line spanned by u. And now we want to consider the reflection along this diagonal. So we want to see what happens to a vector x1, x2 when applying this reflection. So we want to put it here. So maybe it's already clear what this maybe should be. I mean, this length here will be this length, and this length here will be this one. So we will just change x and y, but let's see it by using the formula before. And for this, we now want to write down the matrix of this reflection explicitly. And recall last time that if I have a linear map F, let's say this was a linear map, Rn to Rm, then the matrix of F was given as follows. I can write it down explicitly by evaluating F at these unit vectors E1 up to En. So E1 was just a vector 1, 0, 0, 0. E2 was a vector 0, 1, 0, 0, 0. And En was 0, 0, 0. And then at the end, a 1. So to write down the matrix, we can evaluate this explicitly just at these simple vectors. So let's do this here. So we want to answer the question, what is the matrix of rho u? So rho u is given by, so the matrix of rho u is given by rho u evaluated at E1. And the second column, so it's a map from R2 to R2, so it's a 2 by 2 matrix. And the second is rho u evaluated at E2. And let's see what this, well, let's do this. I mean, what is, first of all, E1 is 1, 0, and E2 is 0, 1. What is rho u of E1? Well, this is rho u of 1, 1, of 1, 0. And by definition, so this is 2 times, maybe let's steal the definition from here. So it's 2 times u times x, so it's E1, and here u minus E1. So what is the scalar product of u1 with E1? Well, it's just 1 times 1, so here it's 1. And the scalar product of u with itself is again 2. What is u? U is 1, 1, minus what is E1? It's 1, 0. So here 2 times 1/2 is just 1. And this will be just 1, 1 minus 1, 0. So this is 0, 1. And with the same calculation, we can see that rho u of E2, well, everything is the same, except, so u with E2 is also 1, this is also 2, so it's the same factor here, and it's also just 1, 1. But then we subtract x, so in this case it's E2, so we subtract E2, which is 1, 0. So the matrix, of rho u, in this case, the first column is 1, 0, and the second column is, the first column is 0, 1, and the second column is 1, 0. So it's this matrix here. Therefore, this map rho u here, so this is rho u of x1, x2. This is exactly given by multiplying with this matrix, which is clear because this is just changing x2 and x1, which you can see in the picture here. So taking the reflection along the diagonal just means I want to interchange x1 and x2. But also this calculation shows exactly this. And yeah, so now we can also ask the question again, what is the image of this? And it is, if it's injective or surjective or bijective. And in this case, the reflection is everything. And because what is the image? We just flip, or we take the reflection along a line, and therefore we stay in the same space. So that the image is everything, because each vector we can reach by the vector which is on the other side of the line, and therefore everything is in the image. So in general, for any n, the image of rho u is always everything, Rn. So in particular, rho u is surjective, but it's also injective, because if I obtain some point by this reflection, then this just comes from one point, namely the other point, the point which is on the other side of the line, and so therefore rho u is also injective. So therefore it's bijective, and therefore it also has an inverse. And what is the inverse of a reflection? Well, it's just the same reflection, because if I send something from one side of a line to the other side, then if I apply the same reflection again, then this point of this side gets sent back to the original point. And this is one part of the homework. So you will show that if you apply the reflection twice to something, then you will get back your original vector. So in other words, the inverse of the reflection is just the same reflection. Okay, now finally, we do some rotation in general. So this is how we started today's lecture. We talked about this rotation by 90 degrees, but now we want to do it in more general. Well, we just do it in R2, so this you can also do in higher dimensions. You can always rotate a raw along some axis, but now we would just do it in R2. And for this first, so what we want to describe is a rotation counterclockwise by some angle phi. And for this, first some basic high school math. So if I have a vector here on the unit circle, and I have an angle phi here, then the length of this side here, this is the cosine of phi, and the length of this side here is the sine of phi, right? If this is the unit circle here. So the length of this is 1. And this you can see because of this triangle here, the cosine of this angle here is exactly this side divided by 1, and the sine of this angle here is this side divided by 1. And therefore this length here is just sine of phi, and this length is cosine of phi. And now let's use this to describe the rotation of a vector x. So here we have a vector x with entries x1 and x2, and we want to rotate this vector by the angle phi. So we want to obtain this vector here, which we will denote by rot for rotation by an angle phi of this vector x. And now we want to find what are the entries of this vector here, depending on the entries of x and depending on this angle phi. And for this, we now also draw this vector here. So this is the one we saw at the beginning. So this, which I call y here, is a vector x rotated by 90 degrees. And this was done by just taking minus the second entry and plus the first entry here. So this will correspond to the rotation of pi half. So pi half corresponds to 90 degrees. So we want to get the coordinates of this vector here. And for this, we can draw this circle here, so it's similar to this situation here. And I almost used the same colors, but I messed up here with the red. So, so we know the coordinates of this vector, and we know the coordinates of this vector. And this purple vector here is this green vector plus this orange vector. And this green vector here shows in the direction of x, but it's not the whole x, but we know the length of this here. Because of this observation here, the length here, which is a number between 0 and 1, is exactly the cosine of this angle here. So if we multiply x by this cosine, then we shorten x in a certain way such that we get exactly this vector here. And if we shorten this vector y, which shows in this direction, and if we multiply it by this sine of this vector, of this angle, then we get exactly this one here. And therefore this vector we are looking for is given by the green vector plus the purple vector, and the green vector is just multiplying cosine of phi with this vector x, and the orange vector is just multiplying this vector y with the sine of phi. So I hope this was not too confusing, but the rotation phi of x is now given by the vector cosine phi times x plus sine phi of y. And what is x? So cosine phi. So x is just x1, x2. And what is y? So y is this rotation by 90 degrees. So this is a minus x2, x1. So we can write this out. So this is cosine phi x1 minus sine phi x2. And here the second entry, so let's maybe write this at the beginning. So it's sine of phi x1 plus, and then this part here, cosine of phi x2. So this is a vector in R2, but this we can now write as a matrix times the vector x1, x2, x1, x2. And here the entry is cosine of phi minus sine of phi, sine of phi, cosine of phi. So we see this rotation here in this picture, this purple vector, can be described by multiplying this vector x with this matrix here. So the rotation by an angle phi is given exactly by this map here. So we define the map rotation along the angle phi from R2 to R2 by multiplying a vector x with this matrix here. And then the matrix of this linear map is given by exactly this matrix here. And you see that when phi is pi half, which corresponds to 90 degrees, then the cosine of, so here is 180 degrees, so here is pi, and here is pi half. So the cosine of pi half is 0. So this here is 0 and 0. And the sine is 1. So here we have minus 1 and 1. And then we see that 0, 0, minus 1 and 1 is exactly the matrix we had at the beginning, which is a rotation by 90 degrees counterclockwise. But this matrix we can use in general to describe this rotation. And this map is also, well, what is the image of this map? Well, we just rotate the whole space, so the image is again everything. So the image of this rotation is R2. So in other words, this is surjective. And is it injective? Well, it's also injective because if I take a point and I rotate it, then this is the only possible way to land at this point. So rot is also, the rotation is injective. So therefore it's bijective. Well, and what is the inverse of a rotation by an angle phi? Well, it's a rotation by an angle minus phi. Or I could also say it's a rotation by 2 pi minus phi. So we have an inverse. So the inverse of this map is given by rotation by of minus phi. Okay. And this is all for today. So we had several examples for some geometric maps. And maybe one of the most important ones is this orthogonal projection. So here we did it now to define the orthogonal projection onto a line. But later we will generalize this and will not just project to a line. So a line is an example of a so-called subspace. We will generalize this projection to project onto on an arbitrary subspace. And this, for example, will have some applications if you want to interpolate some data you measure in your experiment, or also in 3D computer graphics, which I already mentioned before, that if you have a three-dimensional space and you want to show this three-dimensional space onto a two-dimensional plane, then this, like your monitor, so your monitor is a plane in three-dimensional space, and you want to project your scene or your game onto this monitor by using some orthogonal projection. But this we will do at the end of the course. And today this is just a few examples of maps, and with these you will play around in homework 4. Have fun and see you next time.